Okay, this first one up here about swimming pools. What is it about the pool that makes your ears hurt? Pressure change. So as you dive down, the pressure in the pool increases the pressure on the exterior of your ear. So what you have is not so much that there's higher pressure below, but that the pressure inside, on the inside of your eardrum, is not the same as the pressure outside of your eardrum. So that difference is what causes the pain. Because the same situation happens when you drive up Mount Hood, right? It's not that the pressure on the outside is higher, it's that the pressure is different than what's on the inside. So any pressure differential is going to cause that membrane to flex. And that flex, it shouldn't be flexing, so it's painful when it does flex. Boyle's law? What about the pressure and volume? Inverse. So when pressure goes up, then that means volume must go down. And so you should be thinking about like taking a balloon into the swimming pool with you. If you were to dive down into the swimming pool, the pressure goes up. What happens to the size of the balloon? No? It decreases, right? As I dive down into the swimming pool, there's more pressure on the balloon. The interior pressure of the balloon hasn't changed. I haven't added any particles to it or anything. And so because the pressure is unequal, the volume of the balloon decreases. That's like one of the first things, I mean, I haven't been on a submarine, but one of the first things that they do for the new people who are on the sub is they dive down to test depth with a rope. They tie it across the boat. So they tie a rope very tight when they're at test depth, and then they come up. What happens? So what do you think happens to the submarine at test depth, which is the deepest depth that it's supposed to be at? What happened to the balloon as you dove down? It got crushed, right? It got smaller. So the submarine gets a little smaller. Not a lot smaller, but a little smaller. And then they tie a rope from the inside of one wall to the inside of the other wall. So it goes across the submarine. And as they go back up to the surface, what happens to the rope? Eventually it snaps because the submarine has gotten that much bigger. And the rope can't handle it. Gas occupies 12.3 liters at a pressure of 40 millimeters of mercury. What's the volume at a pressure at 60 millimeters of mercury? Okay, so you can either use the equation for this, or I wouldn't use the equation at all. What I know is I've got a liter and a volume, and then I have a new volume. So what am I looking for? What's my answer need to be in? It needs to be in liters because I'm looking for a volume. So I'm going to start with 12.3 liters. And then I'm going to have a pressure over a pressure because they need to cancel out. And then I'm going to be left with liters. Okay, so what did I do to the pressure? Pressure went up. So what's the increase in pressure going to do to the volume of this? Last two questions. It's going to make it go down, right? So my volume is going to go down. I increase the pressure on this object, this balloon or whatever, and the thing gets smaller. So how do I arrange the 40 and 60 to make the 12.3 become a smaller number? Yep, so I'm put 40 here, and I'll put 60 here. The millimeters cancel out, and whatever that 12.3 becomes 8.2 liters. Okay. 600 milliliters of air at 20 degrees Celsius. What is the temperature at 350 milliliters? Okay, so what do I need to do before I start working on this problem? I need to change it to Calvert because the Celsius thing doesn't Doesn't work. So 273, 293 K. So I need a temperature, so I'm going to go ahead and write 293 K here. And I'm going to have a volume and a volume. What did the volume do? The volume got smaller. So if you had a balloon and the balloon got smaller and the only other thing that was able to change was the temperature, what must have happened to the temperature? So it's like taking a balloon and putting it into the freezer. The balloon would have got smaller. So what do I do with the two volume numbers? Put the smaller one on top. So 293 times 350 divided by 600. And I get 171 K. Don't do that. Why is this the answer? I was given in Celsius, then your answer needs to be in Celsius. So this is just a test taking thing. If you're taking a multiple choice exam, guess what? Tell me what answer A is going to be on your multiple choice exam. It's going to be 171K. Actually, sorry, this needs to be negative here. Thanks. And then answer E or D, whatever it is going to be the negative 102 degrees Celsius. So, I mean, that's how multiple choice exams work, right? They're giving you the answer, so you also get a bunch of ways that they're trying to trick you. So don't let, they're expecting if you're given an answer on one particular unit, that the unit comes back as the same, not the correct answer in a different unit. Destiny? I'm turning it back into degrees Celsius. Because that's the equation. If I want to go from Celsius to Kelvin, I add 273. If I want to go back from Kelvin to Celsius, then I subtract 273. Okay, so determine the pressure change when a constant volume of gas at 1 liter is heated from 20 degrees Celsius to 30 degrees Celsius. So first thing, 273, so 293 and 273 to 303 K. All right, so I want to know what the pressure change is, and so my answer needs to have pressure in it. So I've got 1 atm, and I got a Kelvin and a Kelvin, and then the 1 atm, I'm going to need to turn that into another atm. So that's I heat this. So if you heat an object, tell me about this canister for this. Tell me about the container for this particular question. What must this container look like? It's got to be like a solid canister. It cannot be a balloon because this one has a constant volume. So I can only get that if it was like a metal container or something like that. So what's going to happen if I take this metal container that's got a gas in it and then I heat it up 10 degrees Celsius? The pressure, the molecules inside, the gas particles inside are going to start moving faster, hit harder, so the pressure is going to go up. So I'm going to need to make the 1 atm a bigger number. So 303 here and 293 here. And so 303 divided by 293. And we get 1.03 atmospheres. So pressure goes up. All right, what's the final volume of a gas? It's 300 milliliters, subject to a temperature change and subject to a pressure change. Okay, so my answer needs to have units that are volume. So I'm just going to go ahead and start with 300 milliliters here. And then I've got a pressure change. And I've got a temperature change, 273. So 5, 9. So K and 273 So 323K. Okay, so what happened to my volume? Say again? I'm sorry, what happened to my pressure? I don't know what happened to my volume yet. My pressure went up. So what is it, a pressure increase due to the size of a container? Pressure went up, so the container needs to get smaller, right? I'm crushing this container, so it needs to get a little smaller. So I'm going to take my smaller number, my 360, and put it on top of my 750. So that's going to make that 300 milliliter number go down. What about my temperature? What did I do to my temperature? The temp went up. So if I increase the temperature of a gas, what would that do to the volume of the gas? Size. It would make it get bigger. So these two things are fighting each other. That's fine. We know how they fight each other, so it's not a big deal. So now my milliliters of mercury both cancel out, my kelvins cancel out. And so then I've got 300 times 360 divided by 750 times 323 divided by 295. I get 158 milliliters. So it looks like the pressure was more important in this particular case. There was a pretty dramatic pressure change and a very small temperature change, so this thing ended up getting smaller. Questions about those guys?
Yeah, it goes from 750 to 360. Why is that pressure going up?
Oh. Not bad. Yeah. So pressure drops, so this thing should be getting bigger, right? Yeah. So 684. Thanks. Do we have any questions about any of these gas ones? Okay. So we're going to react sodium sulfate with barium chloride, and we're going to produce some substances. And I want you to give me the molecular, full ionic, and net ionic for this reaction. Okay, so then I got to start off with Na2SO4, and I'm going to mix that with BaCl2. And I'm going to get these guys to switch. So I'm going to have table salt, and I'm going to have barium sulfate. Okay, so what happens? Tell me about the states of these things. This guy is soluble because of what reason? The sodium's there. And the sulfate, they both want to be soluble. Tell me about the barium chloride state. Aqueous because of what? Because the chloride wants to be aqueous. The barium doesn't have a rule, but the chloride does, so the chloride wins. This is table salt, so this guy is aqueous because of the sodium and the chloride. And then what about the barium sulfate? Why is that one a solid? That last rule says sulfates are soluble except sulfates that have barium and calcium. So this guy's insoluble. So I've got two test tubes, one with sodium sulfate and one with barium chloride. I mix them together, and then I end up with a table salt solution surrounding a bunch of barium sulfate solid that fell to the bottom. So what does this AQ actually mean? Surrounded by water molecules. Means that molecule is actually already been separated. So there are two sodiums that are positively charged that are aqueous. There's a sulfate with a -2 charge that's aqueous. Then I've got a barium that's aqueous, and I've got two chlorides that are aqueous. Why is the 2 in front of the sodium and in front of the chloride and not subscripted? Because this AQ, remember what that means. We just said that means separated. So when that separates, the sodium that's there, so I've got a sodium and it's attached to a sulfate, and there's another sodium attached to it. That's what the sodium sulfate kind of looks like. And when this goes into water, this breaks, and that sodium goes off and floats away, and that sulfate goes off and floats away, and that sodium goes off and floats away. So if I had written this, Na plus with a 2 subscript, what would that mean? Yeah, that these sodiums, like, I don't know, connected back up with each other and left bonded together, which is definitely not going to happen. Give me a really good reason why that won't happen. They have the same charge. They're both positively charged, so there's no way that's going to happen. So these things need to go off onto their own and do whatever it is that they're going to do. In this case, nothing. Okay, so on my other side, I look up at this, and I've got this sodium chloride. It's still aqueous, so my sodium is still... Oh, we forgot to do something. We need a 2 right here, and that's it. Yeah, you got to balance it. And so then I need 2 Na plus aqueous, and then I've got 2 Cl aqueous. And then what do I do for this last one? I keep it together. Why? Because it is together. It is still connected. They did not disassociate from each other. So I write it down the same. So now what's my goal? What do I do? I get rid of the spectator ions. And which ones are those? This sodium, 2 Na plus AQ, 2 Na plus AQ. So that thing's a spectator ion since it's the same on both sides. Now what? The chloride, 2 Cl negative aqueous, 2 Cl negative aqueous. Exactly the same on both sides. So those didn't react at all. Because the chemical reaction is a change in the formula, right? And there's no formula change for those. They're just sodium ions and chloride ions on each side. So I'm going to write down what's left. And what's left is this barium with a +2 charge that's aqueous, and this sulfate with a -2 charge that's aqueous. And then those things turn into barium sulfate that's not aqueous. That's a solid. So the chemical reaction that happened here was we made barium sulfate. Yeah.
If you put sulfate first, it's okay.
It totally doesn't matter. Yeah. If you had written the SO4 -2 here, it's just by convention I always write the one that's positively charged first, but it's not wrong. Just weird. Go for it.
How will we know if sodium and sulfate is either aqueous or solid?
How do we know that this sodium sulfate is aqueous? Because of the first rule, the sodium rule? Or are you asking how do you know it's... What are your options? What kind of compound is sodium sulfate? No. Tell me what sodium sulfate, what kind of compound that is. It's a salt. It's an ionic compound. And we had a discussion about ionic compounds. So what are your options for ionic compound states? I mean, when we're writing down states for these things, are you ever going to write down a gas or a liquid for these? Like, what temperature do we need to take an ionic compound and heat it to get it to liquefy? Really high. And so we're not dealing with that. And then to boil it, really, really high. So we're not dealing with that. So with these ones that are ionic compounds, so anything that's got a metal in it or a polyatomic ion in it, you know that this thing is going to either be a solid. If it's dry, it's a solid. Or if it's wet and insoluble, it's still going to be a solid. So if it's soluble and it's wet, then the thing is going to be aqueous. So how did we know that this thing was going to be aqueous? No, I mean, how do we know that this was going to be wet? Like, how did I know it? Why isn't this just a solid? Well, I'm telling you this in this problem here that these two things react. Okay, so if I had taken solid sodium sulfate, which to you would look like table salt, and barium chloride, which to you would look like baking powder, and I mix them into a container together, what do you think would happen? Nothing would happen. They're two salts, they're solids. Would the sodium let go to grab hold of the chloride? No, it's already got a negative charge. The barium wouldn't let go to grab hold of the sulfate. It's already got a negative charge. So to make two ionic compounds chemically react with each other, what do you need to do? I got to put them in water to get them to let go. So if I don't do that, then they don't react. So if you wrote down solids for this, it would be a really short problem. It would just be the sodium sulfate and the barium chloride solid, and then you'd write no reaction because they won't react unless they're wet. So these problems where I'm asking you about a molecular, a full ionic, and a net ionic equation, there was the title to this section of the chapter and to this section of the notes. Do you remember what it was? No? Reactions in water. These only happen in water. So when you're looking at this type of problem, you should be like, oh, these are things that are going to happen in water, and I have to think about them being soluble or insoluble. Correct. One side has to be, one of them has to be a cation, one has to be an anion, for sure. What are we doing next? What do we got here? 25 grams of hydrogen reacting with 50 grams of oxygen, and I want to know what's going to run out, what's going to be left in the container, and then how much water is going to be made. So I've got hydrogen, and I've got oxygen, and this is a combustion reaction. So I'm going to make water out of this. What do I need to do to it? I'm going to balance this out. Great. So a couple things. How'd you know that it was going to be water that came out of this? One, I told you in the problem, but two, it's just hydrogen and oxygen, and the only thing that they can make is water. What if it was, instead of hydrogen gas, it was, say, octane, gasoline? What are you going to make? What did you say? Carbon dioxide. So you're going to make, when you do a combustion reaction, if you've got hydrogens and carbons there, you're going to make carbon dioxide and water. That's the easiest way to remember that is that's what you make when you burn sugar, right? It's carbons, oxygens, and hydrogens in the sugar molecule, and when you burn those, you make carbon dioxide and water. So combustion reactions with things that are hydrogens and carbons and oxygens are always going to end up making you CO2 and water. Okay, so I have 25 grams of this, and I've got 50 grams of this. How did I know that it was H2 and O2? Those are the two of the seven diatomics, right? So it'll never just be H's, and it'll never just be O's. Okay, so how do you do this? What do you do first? So in one railroad track, I put 25 grams of hydrogen. I start off this. And then the other railroad track, I start off with 50 grams of oxygen. And what do I end up doing with this? Well, with both of them, I'm going to go to figure out, before I get into the math of these, I'm ending both of these railroad tracks with what? With water. I end them with water because I want to know how much water is made. So when I'm doing these things, I'm always going to pick one product, and in this case, there's only one product, so it's easy. And then I need to figure out how much I'm going to make with each of these two options, with the 25 grams and the 50 grams. So if I've got my 25 grams of hydrogen, I need to put grams of hydrogen down here. So where do I get that number from? So 2.00175, is that right? Actually, I don't know. Let me look. 1.00795 times 2. No, I got that wrong. 159. And then this number, what's the numerator for this number? 1 mole of H2. Okay, so we're going to do the same thing on the bottom, right? So this is going to be 31.9988 grams of oxygen for 1 mole of oxygen. Okay, So for both of these, I've gotten the grams that I started with to be canceled out. And what's this first step do for us? It counts how many hydrogens I have and how many oxygens I have. Okay, so I'm going to need to get rid of this mole of hydrogen and this mole of oxygen. And what I'm going to turn this into is what I'm looking for, which is moles of water and moles of water. What number do I put in here in front of each of these mole units? For the water, I'm going to put a 2. And for the oxygen, I'm going to put a 1. And the hydrogen, I'm going to put a 2. So I just get the numbers there off of the balanced chemical equation. So if we didn't balance this chemical equation, that'd be problematic, right? So I will put a 2 there, and a 2 there, and a 2 there, and a 1 there. Okay, so now I got my moles of hydrogen gas to cancel, my moles of oxygen to cancel. So what I've done here is counted how many water molecules I'm going to be able to make. So first with 25 grams of hydrogen, and then with 50 grams of oxygen. So I need to cancel that mole of water out, because what I need is grams of water, because I can't count that many water molecules. So 1.00795 times 2 plus 15.9994. And so we get that's not right. 18.0153 for 1. 18.0153 for 1. Okay, and so times 25 divided by, this is 223 grams of water. And let's see, we've got 50 times 2 times that 18 number divided by my mass of oxygen, and this is 50, 56.3 grams of water. All right, so what did I just learn? My O2 is going to run out, and I'm going to be able to make 56.3 grams of water. That's what I'm going to make. Can you give me a really, really, really good reason why I'm never going to be able to make 223 grams of water? I don't have 223 grams of anything, right? I only have 25 grams and 50 grams. So the maximum amount of product I could make would be 75 grams, right? But I can't even use all 75 grams. So once I've done this problem, what I've determined is my oxygen is going to run out first. It's okay.
Why you get 350 because 20 grams only 350.
Good point. Good point. We'll just erase that. Is that better?
How about 222?
Doesn't matter because we're not going to use it. It's not part of our answer. It's wrong. Destiny?
So like to get those last numbers like 18, 20, whatever, you're multiplying from you're adding to the oxygen of the atomic number of the periodic table.
The mass of 2 hydrogens.
Yeah.
Yep.
And the same with the oxygen.
Yep.
You're adding to the periodic table of the atomic mass.
This number right here came off the periodic table, and it's the mass of 2 oxygens. This number came off the periodic table, and it's the mass of 2 hydrogens. And this number came off the periodic table, and it's the mass of 2 hydrogens and 1 oxygen.
Oh yeah, because there's 2 hydrogen and 1 oxygen.
Yep. So if I started off with 25 grams and 50 grams, I started off with 75 grams of my reactants, and I made 56 grams of product. So I did not use, whoa. I did not use 19 grams of what? Yeah, how do you know that this is hydrogen? Because I know that this stuff all ran out. Because that's what those two railroad tracks are for, to determine who runs out first. So when this thing is finished, I'll have 19 grams of hydrogen left in a container with 56 grams of water and no grams of oxygen. Okay. How about this next one? There's like a piece of information that is not important. What is it? This is pretty much not an important number. It's only important if I don't have enough. But I got 100 gallons, and so I made sure that you obviously had enough of that. Because I was only looking for you to make 500 milliliters of stuff. So which equation do you use for this one? You guys used it this last week. Sorry, what did you say? Yeah, it's a molarity's in it. No, not molality. The dilution equation. What I've got here is 100 gallons of 6 molar. So I've got this big container of this pretty concentrated sodium hydroxide solution. And what I want to do is make a solution that's less concentrated, and I want to make only 500 milliliters of it. So what am I doing? I'm diluting it. I'm going to take some of the concentrated stuff and put it into a container and fill the rest of the container up with water. So dilution equation. What pieces of information am I going to use here from the problem? That's my starting concentration. This is the volume of what I want to make, and this is the concentration of what I want to make. With all of these problems, I'm going to be looking for what? I'm going to be looking for the volume of the concentrated stuff. So how much of the concentrated stuff do I need to put into the container? Every single time I do one of these dilution problems, that's what I'm looking for. I want to know how much of the concentrated stuff do I need to put in and then fill the rest of the container up with water. So, bless you. All right, so how do I finish this problem? What I write? So after I get this calculation done, what I need to do is, I asked you to explain how to make this. So you've calculated this out that you need 167 milliliters of the 6 molar. So you're going to take that 6 molar, put it in a 500 milliliter volumetric flask, fill near the line with water, and then fill to the line with a dropper. You guys all did that last week, if you were in lab last week. That was part 2 of that question, or that lab.